On September 5th, 2022, engineers at the Space Telescope Science Institute pointed the most sensitive infrared observatory ever built directly at Mars. And for a brief moment, they were genuinely worried it might not work, not because Mars was too faint to see, because it was too bright. The James Webb Space Telescope had been engineered from the very beginning to detect the faintest whispers of infrared light crossing the universe. Light from galaxies so distant and so dim that no previous instrument could ever hope to register it. Pointing that same instrument at one of the closest, most reflective, most thermally active objects in the entire night sky was, in a very real sense, like trying to use a device built to detect a candle flame from 10 miles away to suddenly stare directly into a floodlight. Nobody was entirely certain. Going in, exactly how the telescope's instruments would actually respond, the team preparing the observation spent real time and effort working out exactly how to protect the telescope's own detectors from the very thing they were about to look at. This is the story of how Webb managed to look at Mars anyway, what its first observations actually revealed, and why something as seemingly simple as photographing a planet we have already studied for centuries turned out to be one of the more delicate engineering challenges of the entire mission. To understand why this was ever a problem in the first place, you need to understand what the James Webb Space Telescope was actually built to do. Its primary scientific mission centers on detecting the oldest, faintest light in the universe, radiation from galaxies that formed hundreds of millions of years after the Big Bang. Light that has been traveling toward us for over 13 billion years and has been stretched by the universe's own expansion into extremely faint infrared wavelengths by the time it finally arrives. Every instrument on Webb, and in the entire architecture of the spacecraft itself, from its 21-foot gold-coated mirror to its tennis court-sized sunshield, keeping its detectors extraordinarily cold, close to negative 370 degrees Fahrenheit in its coldest instruments, was optimized around one central goal: maximizing sensitivity to light so faint that almost nothing else in the sky comes close to it in dimness. That kind of extreme sensitivity is precisely what makes Webb capable of studying the earliest galaxies in the universe, and it is precisely what makes studying our own next-door planetary neighbor so much more complicated than it might first appear. Mars is the opposite of that in almost every respect. Sitting, on average, only about 140 million miles from the Sun, compared to the unimaginable distances separating Webb from the galaxies it was actually built to study, distances measured not in millions, but in billions of light years, Mars reflects a significant amount of sunlight directly back into space, and its own surface, warmed by that sunlight, radiates a substantial amount of thermal infrared energy as well. From Webb's vantage point, also nearly a million miles from Earth at the second Lagrange point, Mars appears as one of the brightest objects in the entire sky. Both in the visible light human eyes can perceive and in the infrared wavelengths Webb's instruments were built to detect. That brightness created a very specific, very technical problem called detector saturation. Webb's instruments are so exquisitely sensitive that, without any special precautions, the infrared light pouring off Mars would simply overwhelm its detectors, the equivalent of a camera sensor completely blown out in white, containing no usable information at all, precisely because the instrument was doing exactly what it was designed to do: respond powerfully to incoming light, only now with far too much of it arriving all at once. It is a strange kind of failure mode, an instrument breaking not because it is too weak for the job in front of it, but because it is, in a sense, too good, built with a level of sensitivity that turns an ordinary, everyday planetary target into something closer to an engineering hazard. Solving that problem required astronomers to essentially retrain the telescope's own instincts for this one specific target. Rather than the long, patient exposures Webb typically uses to gather as many faint photons as possible from a distant galaxy, accumulating light over many minutes or even hours in a single observation, the team observing Mars used extremely short exposures instead, deliberately capturing only a small fraction of the light actually reaching the telescope, specifically to avoid saturating the detectors entirely, a technique closer to a photographer stopping down a camera's aperture to shoot directly into bright sunlight than to anything resembling Webb's usual deep field observing routine. They then applied specialized data analysis techniques afterward to reconstruct a usable, scientifically meaningful image and spectrum from those brief, carefully controlled glimpses, essentially rebuilding a complete, coherent picture out of deliberately incomplete individual snapshots. It is worth appreciating how counterintuitive that actually is. An instrument built specifically to be as sensitive as technologically possible had to be deliberately handicapped. Its natural sensitivity worked around rather than leaned into, simply because the target sitting right next door in our own solar system was, from Webb's perspective, blindingly close and blindingly bright. The observations themselves were part of a specific research effort called the Guaranteed Time Observation Program, a category of Webb's operating schedule reserved for scientists who had spent years helping design and build the telescope's instruments, granted early access to a portion of Webb's observing time in recognition of that work. This particular Mars program, formally designated Guaranteed Time Observation Program 1415, was led by Heidi Hammel, a planetary scientist who serves as Vice President for Science at the Association of Universities for Research in Astronomy, and whose research career has focused for decades on exactly this kind of solar system science, the outer planets, their moons, and now, with Webb finally available, our own planetary neighbor as well. Hammel had spent years advocating for Webb's ability to study solar system targets specifically, at a time when much of the public conversation about the telescope focused almost entirely on its deep space early universe capabilities. And this Mars program represented one of the concrete results of that sustained effort, a chance to demonstrate, in practice, that the same instrument capable of studying 13 billion-year-old galaxies could also be turned productively toward the planets of our own solar system. Using its near-infrared camera, known as NIRCam, Webb captured images of a specific region in Mars's eastern hemisphere at 2 different infrared wavelengths on that first observing day. One of those images, captured at a wavelength of 4.3 microns, revealed something Mars researchers found particularly striking: clear variation in brightness tied directly to temperature differences across the visible disk of the planet, changes driven by both latitude and the time of day at each specific location, along with a distinctly darker patch corresponding to the Hellas Basin, one of the largest impact craters in the entire solar system. Its appearance in this particular image shaped by specific atmospheric effects occurring above it. In that same image, a bright yellow region near the planet's center sat right at the very edge of what the detector could handle without saturating completely. A visible reminder, built directly into the data itself, of exactly how close to the technical limit these observations were pushing the instrument. Alongside the images, Webb's near-infrared spectrograph, known as NIRSpec, captured something even more scientifically valuable: a detailed spectrum of Mars spanning a wide range of infrared wavelengths, gathered using 3 separate spectral gratings to cover as much of that range as possible in useful detail. A spectrum like this works by breaking incoming light, apart wavelength by wavelength, revealing exactly which specific colors of light are present, and, just as importantly, which specific wavelengths are missing or diminished, absorbed by particular molecules along the way. The overall shape of Webb's Mars spectrum told its own story even before researchers looked at the fine details, dominated by reflected sunlight at wavelengths shorter than about 3 microns, and increasingly dominated by the planet's own thermal emission, heat radiating directly off its surface, at wavelengths longer than that. Both the sunlight bouncing off Mars and the heat radiating up from its surface have to pass through the same Martian atmosphere on their way to Webb's detectors, and that atmosphere leaves its own fingerprint on both halves of the spectrum in different, informative ways. In Webb's Mars spectrum, that absorption showed up as a series of distinct dips at very specific points, each one corresponding to a particular gas in the Martian atmosphere, pulling out a very specific slice of the light passing through it: carbon dioxide, water vapor, and carbon monoxide, each leaving their own distinctive fingerprint in the data, eyeing dips so clean and so clearly resolved that researchers describe them as easily detected in the earliest look at the raw numbers. Beyond those individual absorption features, the broader shape and slope of the spectrum carried additional information as well, details that researchers could use to learn more about atmospheric dust, clouds, and even certain surface characteristics of the planet layered on top of the specific molecular signatures. By building a carefully constructed model spectrum, adjusting the abundance of each individual gas until the model's predicted absorption pattern lined up closely with what Webb's instrument actually measured. Using tools like the planetary spectrum generator built specifically for this kind of analysis, researchers can work backward from the raw data to precise estimates of exactly how much of each molecule is present in the Martian atmosphere at the specific moment and location the observation was taken. What makes this particular observation scientifically interesting is not that any of these individual ingredients, carbon dioxide, water, dust, seasonal ice clouds, were previously unknown on Mars. Decades of orbiters, landers, and rovers have already documented all of them in extraordinary detail, arguably making Mars the single most thoroughly studied planet in the solar system besides our own, mapped and remapped by missions dating back to the 1960s, with active orbiters, a nuclear-powered rover, and even a small helicopter having operated on or around the planet in recent years. What Webb offers instead is a genuinely different vantage point on an already familiar world, an instrument sensitive across a specific combination of infrared wavelengths, and capable of a specific kind of full-disk spectral coverage that none of the missions actually orbiting or sitting on Mars' surface were ever built to replicate. Spacecraft like the European Space Agency's Trace Gas Orbiter, for example, study Mars's atmosphere in exquisite detail from close orbit, using instruments specifically tuned to detect trace gases and analyze vertical structure, in the atmosphere directly beneath the spacecraft, but from a vantage point that can only ever see a narrow slice of the planet at any given moment, sweeping across different longitudes and latitudes orbit by orbit, rather than capturing the whole visible disk in one observation. Webb, observing from a stable position nearly 1,000,000 miles from Earth, captures the planet's entire sunlit, Earth-facing disk in a single observation, offering a genuinely complementary full hemisphere perspective that no single Mars-orbiting mission can match on its own, effectively trading the close-up, high-resolution detail an orbiter provides for a simultaneous whole-planet snapshot that reveals how conditions vary across every visible region of Mars at exactly the same moment in time. That distinction matters more than it might initially seem. A rover parked at a single landing site can only ever describe conditions at that one specific location, however precisely. An orbiter circling the planet builds up a global picture gradually, one narrow strip at a time over the course of many individual passes, each one separated by hours or days. Webb's full disk observations, taken all at once from a fixed vantage point far outside Mars's own orbit, offer something closer to a single, simultaneous photograph of an entire hemisphere's worth of atmospheric activity, dust distribution, and thermal behavior, a kind of observation that is structurally impossible for any spacecraft actually orbiting or sitting on the planet's surface to produce on its own, regardless of how sophisticated its individual instruments might be. Scientists involved in this research have specifically highlighted several concrete goals this kind of observation makes possible going forward. Now, one is a detailed effort to map the ratio between two specific forms of water molecules across Mars with much finer spatial and temporal precision than has previously been achieved: ordinary water made of regular hydrogen, and a heavier variant called semi-heavy water, where one hydrogen atom is replaced with deuterium, a heavier isotope of hydrogen containing an extra neutron in its nucleus. The relative abundance of that heavier variant compared to ordinary water carries information about the deep history of water on Mars, since lighter, more common water tends to escape a planet's atmosphere into space more easily over billions of years than its heavier counterpart. Gradually shifting the ratio between the two, as a planet's original water supply is slowly lost to space over geological time. Mars today is bone dry on its surface, but abundant evidence, from dried riverbeds to mineral deposits that could only have formed in standing water, shows the planet once had significantly more liquid water on its surface than it does now. Measuring the deuterium ratio precisely, across different locations and different Martian seasons, offers a way to search for any reservoirs of Martian water that might behave differently than expected, whether locked in polar ice, buried underground, or hidden in some other form, potentially revealing details about the planet's climate history that surface missions, limited to specific landing sites, simply cannot capture on their own. A second goal involves studying a very specific, narrow slice of Mars's middle atmosphere, a region existing well above where rovers and most orbital instruments typically focus their attention, using particular emission features from carbon dioxide and oxygen that occur at exactly the infrared wavelengths Webb's instruments are tuned to detect. Those specific emission signatures carry information about how radiation, sunlight, and chemical reactions interact in that middle layer of the Martian atmosphere, and how material moves between different latitudes at that altitude, questions that matter for building a complete picture of the Martian atmosphere from its surface all the way up through its uppermost, thinnest layers, rather than treating the near-surface atmosphere most missions study as though it existed in isolation from what happens above it. A third area of ongoing interest involves tracking Martian dust and water ice clouds directly, monitoring how they shift and vary across different seasons and different regions of the planet. Mars is well known for its dramatic, sometimes planet-encircling dust storms, and for seasonal water ice clouds that form and dissipate as temperatures shift throughout the Martian year, phenomena that existing missions already track in some detail, but that benefit from an additional independent vantage point capable of observing the full disk of the planet at once, at wavelengths specifically sensitive to the presence of these particular kinds of particles suspended in the atmosphere. There is something worth appreciating in just how deliberately incremental this entire effort has been. Webb's very first look at Mars was never framed by the scientists involved as a dramatic, headline-grabbing single discovery. It was framed, correctly, as a careful proof of concept, a first test of whether an instrument built for one specific purpose, detecting the faintest possible light from the most distant reaches of the universe, could be successfully adapted to study something entirely different, a bright, nearby, endlessly complex planet that has already occupied human scientific attention for centuries. The team explicitly described their plans afterward, once these first observations confirmed the approach actually worked, to use the same imaging and spectroscopic technique to explore regional differences across Mars in more detail, comparing data collected at different times and different locations across the planet's surface and atmosphere. That is, in many ways, the real story sitting underneath any accurate account of Webb's relationship with Mars, a genuinely difficult technical problem, solved through careful patient engineering rather than any single dramatic breakthrough, opening up a new complementary way of studying a planet humanity already knows better than almost anywhere else in the solar system besides our own. There was no moment where Webb saw something on Mars that broke the laws of physics. No observation that stunned scientists into declaring the impossible had occurred. What actually happened was quieter, and in its own way more impressive, an instrument built for one extreme, the very faintest light imaginable, successfully redirected toward the opposite extreme, one of the brightest objects in our own night sky without either the telescope or the science being lost in the process. It is worth pausing on why that distinction actually matters, beyond simply getting the facts right. A story built on a false premise, a spacecraft supposedly doing something it never did, a discovery declared impossible when it was, in reality, a difficult but entirely achievable engineering problem might generate a dramatic headline for a day, but it does not hold up to even a few minutes of searching. And it teaches an audience the wrong lesson about how science like this actually works. The genuine story, an instrument built for one purpose, being carefully, cleverly adapted to a second, very different purpose without breaking either the hardware or the underlying physics, is arguably more impressive precisely because it is true and because it reflects the actual patient, unglamorous work that goes into nearly every real discovery this telescope has ever produced. Nothing about Webb's Mars observations required rewriting a single law of physics. What they required was a team of engineers and scientists solving a specific, solvable problem, carefully, correctly, and in full public view, with every step of that process documented and available for anyone curious enough to go looking. Webb continues to periodically return to Mars as part of its ongoing solar system observation programs, adding new data to compare against that original September 2022 baseline, building, slowly and carefully, a longer record of how the planet's atmosphere and surface conditions shift across Martian seasons, the same patient, incremental approach that has defined nearly every one of Webb's genuine solar system discoveries since it first opened its instruments to the sky. That approach will never produce a headline claiming the impossible has happened, because nothing about it is impossible. It is simply careful, ongoing science conducted by an extraordinary instrument pointed at a planet we have been trying to understand for centuries and are still, patiently, piece by piece, continuing to learn more about. If this is the kind of story you want more of, subscribe and let me know in the comments what you'd want Webb to look at next, right here in our own solar system.